That's the good news. The bad news, I can't help resist. I just tweeted it. I'm very upset because I just got news that the Saudi courts have reaffirmed the 1,000 lashes and made the final judgment. It can't be subject to, and the 10-year imprisonment sentence for Raif Badawi. So I said, although I agree with Jerry that the Supreme Court, the judges in Saudi Arabia don't have free will, they are nevertheless barbarian savages, and we should. I don't know how we can boycott Saudi Arabia, but we should, and we should certainly protest, although they expressed surprise that anyone was protesting. But anyway, okay, but so that bad news, one of the reasons we do cosmology talks, there's a bunch of things I want to do today that show something about the nature of science as well as confuse you. But one of the reasons is to avoid the crap we have in the current world. So cosmology is great because unlike questions of free will, which are pressing and urgent, we can worry about the universe, and it takes us away from our normal things. So I think the point is, it works. Okay, good. I can hit this, and it worked. So it's the best of times, and by that I mean that the Large Hadron Collider is turned on. Okay, and it hasn't destroyed the world with a black hole yet. Oh, there's my pointer. And of course, at the same time, it's the worst of times. Let's see. Yeah, no, actually, that's not the one. Neil Tyson is a friend. I guess he amuses me. This is the next president of the United States, this is the most surreal, one of the most surreal moments I've had in my life. When he approached me at a meeting that I was at the World Economic Forum in China, and he thought I was someone important, and he wanted a selfie. So I agreed, but it was kind of weird. Anyway, and he's just as stupid in person as he is just in case you're wondering. But I'm very friendly. I'll give him that. Anyway, but the purpose of going back to the universe is to get away from worrying about Rick Perry, because it doesn't really matter to the universe. So I want to go back in time, and I always can't help but show these Hubble. This is one of the more recent Hubble pictures. It's a multi-chromatic image. It's many different colors. It was just produced a few months ago. So it's one of the deepest images that shows by real color which galaxies are. And every image in that, except for one, every dot in that image is a galaxy, not a star. Okay, so these are galaxies that go back to almost 10 billion light years away, and every dot there is a galaxy, and that's the kind of thing that causes me spiritual awe and wonder, because many of the light from those galaxies was emitted 10 billion years ago. And our sun was only going to last about 10 billion years. So if you look at it, many of the stars in that image no longer exist, and the civilizations around those stars, which had beings that didn't have free will, no longer also exist, and it amazes me. But when we try and look at the universe, it makes us think, of course, of questions of origins, which is of great interest to me. And one of the neat things about the universe is that thinking about those questions ties together the biggest scales on the universe and the smallest scales. This is one of an image that's almost it goes back 4,000 years. I'm not going to carry this, even though I like the idea of walking around with it, just to prove I can do that. Okay, here we go, almost. This is something called an Ouroboros. In different cultures, it's different things. It's a snake that eats its own tail. This doesn't look like a snake because it has legs, but it's evolved. And it was Shelley Glashow, a physicist friend of mine, who first sort of suggested this. But the point is, because the universe is expanding, it was once smaller than it is now, and it was smaller still. And if we want to understand the conditions that led to the largest structures we see in the universe today, like those galaxies, we really want to understand the small scale. So as we try and understand physics on different scales, from human scale up to the Earth, planets, galaxies, and clusters of galaxies in the universe, ultimately we come back again to that earliest moments of the Big Bang, to the really fundamental forces that govern nature, which is the reason why I got interested in this field in the first place as a particle physicist. And that wonderful connection between the very largest and the very smallest tell us that we can learn by looking at large scales something that tells us about our fundamental makeup. and the laws that govern our existence. And so when we do that, we want to look back as far as we can see, because the further back we look, that we're looking at earlier times the universe was smaller and smaller and smaller. But when we look out at the universe, the farthest back we can see is there. This is the cosmic microwave background, the radiation coming at us from the Big Bang, and that's as far as we can see, because when we look back at the universe, before the time when this was created, when the universe was 300,000 years old, the universe was opaque, so we can't see past that time, like we can't see past these walls. And so what we look out as far as we can see those galaxies and et cetera, the earliest galaxies, and then if we look out, we can see back to the time when the universe was 300,000 years old, and then we see this sphere, and this is a sphere in the same sense that this is a sphere. Actually, it's upside down. There we go. And my wife's from Australia, and I spend a lot of time there, but so we're northern hemisphere centric. But when we make a projection of the sphere of the Earth, we do that, and that's what we've done here. We've just made a projection of the whole sky, and these are microwaves, and these are temperatures. So the hot spots and the cold spots are different temperatures, very small deviations in temperature. The difference between one color and another here is about 1/1000th of a degree. The overall background is about 2.74 degrees above absolute zero. It's the smoothest background you can imagine. The universe is incredibly uniform in all directions. One of the biggest mysteries, actually, that we're trying to solve. Why is the universe the same over there as over there? Because, in fact, when the universe was 300,000 years old, light could have only traveled about what is now the equivalent of 1 degree on this surface. So nowhere over here could have known anything over there was in existence. Why are they the same temperature to 1 part in 1,000, or almost 1 part, in 100,000? And at the same time, where do these little lumps come from, these hot and cold spots that would eventually collapse to form everything we see today, to form all the stars and galaxies? These are the primordial lumps that were potentially put in at the beginning of time. Where did they come from? Also, by the way, when you look at this is the stuff in the center is the plane of our galaxy. And you have to get rid of that if you want to go back to the real primordial lumps. And normally I wouldn't show that, but the plane of our galaxy will become important in a bit. But we can do manipulations on this and try and subtract the galaxy. And then this is the image, the primordial image from the most recent Planck satellite, which is a microwave background satellite that's gone and looked at the entire sky. And those are the hot spots and cold spots that we want to understand. But we're stuck. That is pretty late in the history of the universe. 300,000 years is pretty late. We want to go back earlier. But we can't ever go back earlier if we're using light, because we can't see back before that time. So if we want to go back earlier, we have to use something that can get through the universe from the beginning of time to that moment, okay? And that means we have to use stuff that interacts less strongly than light, okay? And what we can use is, in fact, something that interacts very weakly. In fact, it's gravity. Gravity is the weakest force in nature. Most of us don't appreciate that when we wake up in the morning and try and get out of bed because it's gravity, or climb the stairs. But that's because the whole Earth is attracting every atom in our body. Gravity is unbelievably weak. And Einstein, when he developed general relativity and showed that matter and energy curve space, also recognized that when you wave your hands, like I do a lot, we're producing a disturbance in space, and that disturbance in space propagates out. It's not just a disturbance in space, it's a disturbance in space and time. And when I do this, I create something called gravitational waves. Just like when I shake an electron in the stuff that this microphone is connected to, it jiggles the electrons, and that creates an electromagnetic wave which goes to the back of the room and gets amplified, and then you can hear my voice. So electromagnetism is when I shake electrons. When I shake any mass, when I move any mass around, I produce gravitational waves, and there are many of them in this room right now, going right through you. The thing is, gravity is so weak we can't detect gravitational waves. But I'm going to show you what a gravitational wave looks like. It's wrong thing. Let's see if I can do this. Okay, so if a gravitational wave was coming out of these screens, okay, then this is what would be happening. Literally, when a gravitational wave goes through this room, it changes lengths. the length of the room will get a little smaller in this direction and a little bigger in that direction, and it'll oscillate, okay? Back and forth. That's what a gravitational wave does. And that's happening all the time in this room. But they're so weak, we can't detect them. And in fact, we haven't yet been able to detect them directly. They're so weak. I'll show you the best gravitational wave detector we've ever built. But this is a three-dimensional version, if you like it. It looks like a snake, but three-dimensional things never are understandable. But that's what it would look like if it's propagating out. And so we would like to, Einstein predicted them actually in 1917, and then by the way, I know Jerry was being facetious, but Einstein was wrong a hell of a lot of times, not just never. One of the many things he was wrong about was gravitational waves. He predicted them, and then he thought they didn't exist, and he wrote a paper saying they didn't exist, and happily, the peer review process saved him, although he was never, it turned out he discovered he was peer reviewed, and he got so mad. He'd never been peer reviewed in his life before or after, not once. He objected so much to the process that he withdrew the article and refused to ever submit to that journal again when he found out that they dared to send his work to anyone else to read. It's an interesting thing. I just wrote an article for Scientific American about Einstein's mistakes, and I discovered that. It was kind of amazing. Anyway, that's got nothing to do with this, but it's amused me to tell you. So if we could detect gravitational waves, they're so weak that they could actually make it from the beginning of time to here. And that's what I want to talk about, because this may give us an empirical handle on the beginning of the universe and far more. So I said gravitational waves are extremely difficult to detect, and this is the biggest gravitational wave detector we've built so far. It's the LIGO Interferometric Gravitational Wave Observatory, and there's one of these in Hanford, Washington, and another one in Louisiana. And they're designed to detect gravitational waves from, so when I move my arms, I create gravitational wave, but my arms aren't very massive, so it's not a very strong wave. So we try and look at the most cataclysmic processes we can see in the universe and hope that they produce gravitational waves, and some of the things that might do that are colliding stars, or colliding black holes, or colliding neutron stars in our galaxy. And so this detector was built to try and detect events from these cataclysmic things when two massive objects, 1 million times the mass of the Earth, collide. But they have to be incredibly sensitive. And this amazes me, because this is the kind of stuff that science fiction would never write about, or theologians. So there are two arms here. You can see all of both arms, but there are two arms. They're 3 kilometers long at right angles. Okay? And if a gravitational wave came down from above, then one of the arms would get a little bit shorter and one of the arms would get a bit longer, and then it would change, right? Okay. So you can calculate how sensitive these have to be in order to try and detect gravitational waves from two stars colliding in our galaxy. And it's kind of amazing. It's amazing to me that this works, because what they can do right now, what can be done right now, is with these detectors, they're designed so you can detect a change in length of this 3-kilometer arm. We send a laser beam down that direction, a laser beam down that direction, and reflect it and see if they come back at the same time, basically. And right now, the sensitivity is such that you can detect a change in length of these two arms, 3 kilometers long, by an amount 1/100th the size of a proton. You should do that. It's amazing. I mean, it amazes me that it can be done. I just never thought it would be able to be done. It is remarkable. We actually use principles of quantum mechanics to try and do this. The sensitivity here is so amazing that when a truck drives along like 50 miles away, it would produce a bigger disturbance. So you've got to insulate this from those kind of sonic disturbances. It's amazing that you can isolate all those processes and do it. But this machine works. It hasn't detected any gravitational waves yet, though, because apparently it's not sensitive enough. So it's actually been improved. It's being improved right now, and it's going to come online in the next few years. It'll be improved so it can detect a variation about 1/1000th the size of a proton. And we're pretty certain at that level we should see lots of events of stars colliding in our galaxy or maybe other galaxies. But we've never seen gravitational waves directly in this sense from these things. But it turns out that there's another source of gravitational waves which some people thought they had detected, and we may have detected it, you'll see. And that is the universe itself. Because as cataclysmic as colliding stars are, that's one thing. But the Big Bang itself is pretty damn cataclysmic. And it turns out the Big Bang, in a very specific way, produced gravitational waves that I want to talk about and tell you what we can see if we see them. This detector claimed to see gravitational waves. This is a detector called the BICEP detector. It's at the South Pole. It's actually a microwave background detector. It's looking at that cosmic microwave background. But what it claimed to see was the imprint in that cosmic microwave background of gravitational waves that had traveled from the beginning of time and left a signal that I'll tell you about. It's a kind of an interesting thing to build a detector at the South Pole. It kind of amazed me when I learned the limits. After all, we can go to the moon. Well, that was faked. But we can go to the deep oceans. We can go all these places. But you can't really travel to the South Pole other than during the summer in the South Pole. This is setting up. There's another telescope, the South Pole telescope, next to BICEP, and this is a big cargo plane. This is delivering liquid helium to these detectors, which you do in the summer, because although the South Pole is cold, it's not cold enough, and liquid helium is a few degrees above absolute zero, and so this is delivered during the summer because you can't fly down to the South Pole in the winter. And it surprised me when I first learned that, because it's just the rule. So that means. This is an interesting picture I want to show you. It's one of my favorites of BICEP. This is a picture of BICEP at sunset, which, if you think about, is an amazing picture because sunset happens once in the South Pole every year. So the minute the sun goes down, it's winter and it's dark and you don't leave. So undoubtedly the person who took this picture was a graduate student because those are the people we send down for the winter in the South Pole. And they have to have special tests to make sure they can survive. This is another thing that's entirely irrelevant, but I can't resist telling this audience. So one of our students went down there and was there, and the test they administer, he claimed, was the same test that the armed forces used to do to see if you were gay. And I don't understand that at all, but anyway, that's what they did. Okay, so the BICEP detector made an announcement a year ago. In March a year ago, that astounded the world because they claimed to see gravitational waves from the Big Bang. So let me see. So I want to give you a little bit of where these come from. It doesn't tell you very well, but so we have this. Remember, one of the paradoxes I told you about is the fact that why is the universe the same over there as over there? To a 1 part in 100,000 if those regions could never have communicated with one another. That's been a paradox we've been living with for over 40 or 50 years, well, actually over that, but it was really recognized about 50 years ago that was a real problem with the Big Bang. Unless God set it up to be that way, how could it be that way? Okay? And so we, of course, got rid of God in that sense by recognizing that there's a physical process that can make that happen. Not only can it make it happen, all of our ideas from particle physics suggested it should happen. Namely, at very early times, the universe, energy gets stuck in empty space in the universe. And I'll talk about how that happens in a second. Or not in a second, a few minutes actually. But energy gets stuck in empty space, and that causes the universe to expand very fast for a very short time. And this period is called inflation. And if it happened, the universe expanded by a factor in volume of 10 to the 90th, that's 1 with 90 zeros, in a time period of a millionth 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 of a second. It sounds like science fiction, but when the universe was 10 to the minus 35 seconds old or so, for a very short time, the universe puffed up by a huge amount, and then inflation ended, and then the regular Big Bang, continued. Now, what would that do? That would mean that two regions which are now very distant, if you work back, were always further away apart than light could have traveled, were actually once much closer together before the expansion. And that means they could have communicated to one another, and the universe could have become, uniform, and then it puffed up, and then underwent its stuff. The other interesting thing is that during this period of puffing up, quantum mechanics is very important in causing the universe to expand very fast. It's energy in empty space, and there are quantum fluctuations about the energy in empty space. And we can actually predict what they would do, and they would produce small variations which look just like the variations in the cosmic microwave background radiation. So that suggests that not only does inflation happen, it suggests, it doesn't prove it, it suggests it happens, But it also tells us something really interesting, that we are actually here, we're quantum mechanics in action. We often talk about quantum mechanics happening over very small scales. But the lumps that eventually became the galaxies and stars and planets and aliens and people were there because they began as quantum fluctuations. So we are the direct result of quantum mechanics, operating at a macroscopic scale. And it is remarkable if it's true. It is so remarkable we want to find out. But during this period, inflation predicts many things, and the problem is it's very malleable. It's an interesting idea. But it could be compatible, even if the lumps we see in the microwave background were slightly different, an inflation model could predict that. So if you can predict something that agrees with anything, it's not a prediction at all. So, just being consistent is not what science is all about. It's being falsifiable. And so the question is there a prediction of inflation that is sort of unique, ubiquitous, and falsifiable? And the prediction is gravitational waves. During that period of expansion, when there are quantum fluctuations, if gravity also responds to quantum mechanics, there should be quantum fluctuations in the gravitational field, and that would produce gravitational waves of a very specific type. And that's what we've been looking for. And that's what the BICEP experiment claimed to have seen, in March of last year. This is a complicated image, but it was from a Scientific American article I wrote a year ago, so I spent endless amounts of time trying to get the artist not to make mistakes. So I thought, even though it's incomprehensible, I'd show it. But I'll give you a heuristic argument. So this is the idea. So this is the sort of universe. There's a big bang, there's a rapid period of inflation, and then the universe expands, and then there's the microwave background, and then today. So this is a time history. We'll start there, and then I'll go here for all the rest of you. So we start there, and there's a rapid period of expansion. And during inflation, gravitational waves get produced, start oscillating, but then they get stretched out during inflation, and they stop oscillating because their period is longer than the age of the universe. So they just get frozen in. Then inflation ends, and what happens? Well, the smallest wavelength, highest frequency gravitational waves start to oscillate because their period is now shorter than the age of the universe, so they can actually start to oscillate. And so what happens is after inflation, I'll show you guys here, after inflation, the shortest gravitational waves start to oscillate. But as the universe evolves, gravitational waves die off. So the shortest wavelength waves, gravitational waves die off. Then there are longer wavelength gravitational waves. They start to oscillate later in the history of the universe. And they start to die off. But there are long enough wavelength gravitational waves that their period is, say, 300,000 years. And they don't start to oscillate until the time in the universe when the universe is 300,000 years old, just the time when the microwave background is being created. And those gravitational waves will produce an imprint on the microwave background. I'll show you, I think I have it, in this image. So the microwave background is caused because radiation is everywhere and it's interacting with electrons and it gets scattered to us. And then the universe becomes neutral and those free electrons get captured and they stop scattering, and so that radiation can come to us because the universe becomes transparent. So the minute that surface, the last moment of that surface is when the last radiation scatters off an electron and comes to us. Now, if the universe is uniform, the electron sees uniform radiation coming at it in all directions. But what if a gravitational wave of very long size, the size of the visible universe for that electron, comes along? What it'll do is it'll shrink the universe in one direction and stretch it in another. And that means the electron will see a universe that's shrunk in one direction and stretched in another. Well, that means that the intensity of radiation will be greater coming from this direction than that direction. And that means the electron will scatter radiation preferentially in one direction, radiation that's oscillating in one direction rather than another. It'll produce what we call polarized radiation. Polarized radiation is just electromagnetic waves that are just oscillating in one direction rather than another. That's why you get polarized glasses when you're fishing, because the sunlight comes up and it reflects, but that reflected light is polarized, and if it's oscillating in this direction and your glasses only see radiation oscillating in that direction, you won't see the reflected image, so you won't see the glare. That's why you can fish with polarized lenses, okay? So the bottom line is that there'll be a signal of polarized radiation if there are gravitational waves, and it's a very specific kind of signal. It's not easy to see, but I'll show it to you. For example, here is an image of the microwave background, and I put random polarizations, because if there's no gravitational waves, then the electrons are oscillating in random directions. And this is what it would look like if there were gravitational waves. You can't see a difference. Okay? It's really, really hard to do, but the people try and do it. And the BICEP experiment, I think, did a simulation, which I hope I have. This is what they thought things would look like. The thing about gravitational waves is they produce these snake-like patterns, almost like Ouroboros, of polarization in the microwave background. So you predict these very particular kind of polarization, snake-like waves where things are moving around, sort of going around in a circle, as you can see. That was the prediction. March 17th, maybe St. Patrick's Day, the BICEP experiment published this result. This is what they saw in the microwave background. And this was astounding, because if this is true, this is, in my opinion, literally perhaps the most important image that science has ever produced. Because if it's true, this is, first of all, the first direct detection of gravitational waves. And secondly, this is an image of stuff that was created not when the universe was 300,000 years old, but when the universe was a millionth of a billionth of a billionth of a billionth of a second old. This is an image directly from the Big Bang. And therefore, if you think about it, it pushes our window of the universe back by a factor about 10 to the 49th. I mean, when you prove things by an order of magnitude, it's pretty good in science. But if this is true, it pushes our window back to the history of the universe by 49 orders of magnitude in time. And therefore, it's profoundly important because it allows us to directly test ideas about the beginning of the universe. And that's important if you want to turn metaphysics into physics. Okay? So this was profoundly important. Unfortunately, it might not be right. And I'll show you why. This is, I want to show you a graph, but it doesn't really matter. So this is if you look at these things, you'll see a little bump here. This is the signal that they claim to see. It doesn't really matter what this is. This is really a strength of polarization as a function of degrees across the sky. And you see the bump. All these other curves are the noise, the expected noise, which you have to worry about in science. Because there's always noise, there's always background, there's always uncertainty. And what's interesting is, what is amazing to me, and what was amazing to me when I first saw this, is not that it's just there, but there's a dotted line there, and that's the prediction from inflation. If inflation happened, this should have this specific character, and it has it. And it was just amazing. And it was way above the noise. This noise comes from a lot of sources. Lots of things in the universe between then and now that get in the way. Just like, remember, you saw the picture of the cosmic microwave background, you saw the galaxy in the center? We had to subtract it out. The galaxy is between us and the microwave background. Well, the galaxy contains a lot of things. Most importantly, it contains dust. And dust can get in the way, and dust can be polarized by magnetic fields and electric fields. And therefore, if the radiation scatters off dust in our galaxy, it'll get polarized. So it can be a background. So, but they said, look, we can figure out how much dust there is in our galaxy. We think we know how much there is, and it's not enough. Well, the Planck satellite that I showed you earlier, that showed the cosmic microwave background, actually is better able to look at this because it looks at the entire sky. This was a small region of the sky as seen from the South Pole. But the Planck satellite looked at the microwave background over the whole sky, and they said, we can kind of estimate how much dust there really is. And a couple of months after this result, they came up and produced a paper that said, well, you know what? Here, sort of this little bump here, if you look at it here, the first bump, is that bump there. So this is kind of the prediction of gravitational waves for inflation. This is what they saw. But what the Planck satellite said is, well, all of this shaded region is what dust could do. The galaxy is much dustier than we thought. And dust could produce, within this uncertainty, this much of a signal. And up here, you see, it could produce a signal that's comparable to the signal that was seen. Now, the dust would produce a flat line, and this signal is up and down, which is one of the reasons I found it a little compelling. But they said, look, extraordinary claims require extraordinary evidence, as we've heard everyone say. It wasn't Carl Sagan who said it first, but he popularized it. And it's true, and this is perhaps the most extraordinary claim that science has ever made. So you better be absolutely certain it's not background. And then this is really interesting to me, because here's the difference between science and theology, or whatever you want to call it, religion. Because the Planck people really wanted the bicep people to be wrong, because for a number of reasons. One is they wanted to make the discovery, and because it's going to win a Nobel Prize or two. Okay, so they really wanted them to be wrong, and these guys really wanted to be right, and they wanted them to be wrong. So what did they do? Each of them had their, if you want to call it ideologies, people who claim scientists have ideologies. Each of them felt that their experiment was right. And so what did they do? They didn't go out, and the bicep people didn't go and cut the heads off of the people from Planck, and vice versa. Yeah, they may have wanted to, it's true, but they didn't. The difference is what they do. They said, let's get together and do an experiment together and figure out who's right. That's the difference. Because what they cared about was what the answer was, not what they wanted the answer to be. And that's a profoundly, so even this is, yeah, you should all applaud. Because, so in February of this year, the two experiments actually did combine together and reported a result, and I'll read it to you. It says, the original experiment, that was this thing, found that the level of, that's the Planck experiment, found that the level of dust power in a field centered on the bicep region, but somewhat larger than it, is the same magnitude as the reported excess, but noted that the present uncertainties are large, and that a joint analysis was required. And so then they wrote, in this paper we performed this joint analysis. So the two groups got together. And what did they discover? Well, they discovered there's a lot more dust. This is a likelihood. This is the result. This is the likelihood, this number R at the bottom, which you can't even read. If it's 0, then there's no gravitational waves. If it's non-zero, there isn't. And this is the likelihood that, the combined analysis finds that of R. And you notice it's peaked at non-zero. Okay? But it's fairly close to 0. If I put on the same scale, and I couldn't, I had to expand the original paper so that R of 0.1 was the same in both places. This is the original bicep observation. And you see it's just much bigger than that. Okay? But again, this is the power and importance of understanding, of making claims in science. So this is what the result is. The final result is expressed as a likelihood curve for R and yields an upper limit, doesn't matter, at 95% confidence level. It peaks at a non-zero value, but disfavors 0 by only a factor of 2.5. This is expected by chance in 8% of the universes, basically, as confirmed by simulations in a dust-only model. We emphasize that this significance is too low to be interpreted as a detection of primordial gravitational waves. So what this means is 92% of the time, if this result is right, 92% of the time, that would imply their gravitational waves from the Big Bang. But in 8% of random universes, it would just be an accident. And in a lot of fields of science, unfortunately, and in a lot of fields in the rest of it, 92% would be enough for you to say it's there. I have a 92% belief that I saw a ghost yesterday, okay? Or that God talked to me. But in science, in this kind of science, for this kind of important result, 92% just doesn't make it. So when you actually read this quoted in the popular literature and by scientists, you won't read that there's a non-zero result, even though the curve peaks at it. You'll read that there's no evidence for gravitational waves, that the original claim was wrong. Okay? It may not be wrong. It could still be right. We need to do further experiments. And that's what's interesting. It may be on the threshold of being detected. And I want to talk to you about what would be the case of the implications if it were detectable, because they change everything. They allow us to explore aspects of the universe and indeed beyond our universe and the beginning of time in a way that makes many of the things I talked about in my last book that may have seemed metaphysical actually testable. And I find that fascinating. So I want to talk about what the implications of those things are in the last bit. Okay, to do that I have to explain what inflation was in a little bit. Inflation is like when you, in the wintertime, which you experience here, if on the roads, some of the things that may be dangerous is in a day where the temperature is changing very fast, okay, and there's water on the roads, and then it goes way below zero, and it eventually turns into ice. But there's still water on the roads, right? Because it's getting sloshed around and stuff. So the water is far below freezing, but it's still liquid. Okay? That's what's called a metastable state, because what can happen is, bam, the water can suddenly freeze. And when it does that, by the way, it releases energy. The temperature of the water, even though the day is cooling, the temperature of the water remains constant, because energy is released as water goes from its disfavored phase, liquid, into ice. It would rather be ice, and as it moves from one to another, it releases energy. So the temperature of the water remains constant. That's what we call a phase transition in physics. And a more poignant example, which will become relevant, is if you look at the frost on a window on a winter morning, you'll see all sorts of beautiful icicles pointing in random directions, because at each place the water froze and the icicles get put in a random direction. There's no governing it. Okay? They're all random. Think about that for a moment, because it'll be important. Because while we can see that they're all random, if you lived on one of those icicles, one direction in your universe would be very special. The direction of the icicle. And as far as you're concerned, that would be a very special direction. But it's random if you can see all the icicles. Okay? So what turns out we can predict is, in the early universe, we think that all the forces, non-gravitational forces of nature, were unified in something we call a grand unified theory, and the reasons I'll show you to think that exists. And then, at some point, as the universe cools down, that becomes a disfavored state, when all the forces look the same, and some of the forces want to look different. It's called a phase transition. We know that happened, by the way, because it happened much later in the history of the universe, when the universe was only a millionth of a second old, and at that point, electromagnetism and an interaction called the weak interaction, which originally looked the same, begin to look different. And that's a phenomenon we're exploring at the Large Hadron Collider right now. Okay? We know that really happened. They originally were just the same force. Electromagnetism and the weak force, which governs nuclear reactions in the sun, were once the same force and looked the same, but they started to look different. They started to look different as the universe cooled, and the favored state was for them not to look the same anymore. We think that happened at a much earlier time, when all three non-gravitational forces came together, when the universe was a millionth of a billionth of a billionth of a billionth of a second old, for reasons I'll show you in a second. And then the universe, what could happen, and what Alan Guth realized could happen, is as the universe cooled, if it was cooling fast enough, the universe could get stuck in this metastable state where all the forces were looking the same before it relaxed into this new state, just like water to ice. Okay? But when it gets stuck in that metastable state, energy is stored in empty space. And when you store energy in empty space, it's gravitationally repulsive. It's not attractive. It's what's actually, I think, for a different reason, happening today. And that means during that time, it would cause this incredible expansion of the universe, which is called inflation, but then that expansion would end, just like when an ice crystal forms. Some seed would happen, and there'd be a phase transition in some region, and that phase transition would leave that accelerating phase, and all that energy would be released that was stored into particles and radiation, causing the Big Bang we see now. Okay? And that's what this picture is just saying, we call it a false vacuum. For a while, the universe got stored in that, it got stuck in that metastable state, and then it eventually left that metastable state, and boom. And that's inflation. That would happen if all the forces in nature, other than gravity, were unified at that time scale, and we have a reason to think that they should be. We can measure the strengths of the three forces in nature, other than gravity: the weak force, the electromagnetic force, and the strong force. And back in 1970s, we could measure them relatively poorly. This is the scale we measure today. But one of the most amazing things we've discovered about nature is that the strength of the forces change with scale. Electromagnetism, as you get closer, actually gets stronger. Not just the 1 over r squared force, but the actual force itself gets stronger. One of the great discoveries that surprised everyone in the 1970s was the strong force, the force between quarks, which is the strongest force we know in nature, actually gets weaker. As you bring quarks closer together, the force between them gets weaker. It was a huge surprise, something called asymptotic freedom. It was predicted in 1973 and it basically discovered, and eventually in 2004, my friends Frank Wilczek and other people won the Nobel Prize for that discovery. So the strong force gets weaker and the weak force gets stronger. Well, that's a hint that maybe if we go to ever smaller scales, these two forces, which seem very different on our scale, if we look on very much smaller scales, they'll begin to look similar. And the weak force does too. A weak force gets stronger as well. Well, that was a great idea, and it suggested we could do wild extrapolations from what we could measure in the 1970s. And that suggested that if we went to a scale 16 orders of magnitude smaller in size than the size of a proton, maybe all the forces would have the same strength. And that was called grand unification. There was a lot of excitement about it. Unfortunately, it doesn't work. It's a good idea, but it doesn't work. Most good ideas don't work. Okay, we don't publicize that, but it's true. If they did, anyone could do physics. Okay. So we can now actually measure these forces. We can measure what they do, and they don't come together at a single point. If all the particles we measure are all the particles that exist. But for other reasons, which I really won't go into, well, I'll be happy to in the question period, we think that actually there's new stuff that's going to happen at the scale of the Large Hadron Collider. That's why that's why we've turned it on again. There's a new symmetry of nature which we think will help us explain some things we don't understand. It's called supersymmetry. It predicts a whole bunch of new particles. And those new particles will change the nature at which the forces, the rate at which the forces change as a function of scale. And when you plug them in, if you assume supersymmetry exists, and you plug them in and do the mathematics, what do you find? All the forces come together at the scale almost 16 orders of magnitude smaller than the size of a proton, or if you wanted to probe that with energy, 16 orders of magnitude in energy higher than the mass of the proton. Incredible. We'll never be able to see that directly. With the Large Hadron Collider, we can, at best, explore here 14 orders of magnitude in scale larger than that time. So you might think we'd never be able to detect it. But what's interesting is, if you ask what scale that corresponds to, when was the universe that dense, when those kind of energies existed? When it was a millionth of a billionth of a billionth of a billionth of a second old. So if grand unification happened, and inflation happened, it should happen at a time when the universe is a millionth of a millionth of a millionth of a billionth of a billionth of a billionth of a second old. And it turns out, if you do the calculations, it should produce gravitational waves of a scale that might be detectable at BICEP. So that's one of the reasons that gravitational waves are such an amazingly important tool. If they're really there, we are probing physics at a scale 14 orders of magnitude smaller in size, 14 orders of magnitude more in energy than the Large Hadron Collider. Greater in energy than we'll ever be able to explore here on Earth. To produce an accelerator of that kind of energy would require a radius greater than the Earth-Moon distance. And I don't think that the NSF of the future will ever approve that. They won't even approve they wouldn't even approve a damn machine in our country. We were going to build the Large Hadron Collider. It was called the Superconducting Super Collider. We were building it in Texas in 1993, but Congress, in its immense wisdom, and by present standards, it does seem wise back then, but said we couldn't afford it because it was $6 billion. So we couldn't afford to build this thing that would probe the fundamental structure of nature. That's like the air conditioning bill in Iraq in a week, okay, during the war, but we couldn't do it. So we didn't do it, and it's now being built in Europe, but that's okay. But it would be great. That's why gravitational waves are so important. But if gravitational waves are sort of iffy and there's backgrounds, we got to ask, is there another place we could explore these things? And the answer is, it's not the only place we might get a signal. There are other wonderful experiments that we're building. Sorry, it's not this, it's this. That we're building. This is one of my favorites. This is in Japan, in the Kamioka mine in Japan. This is the Super Kamiokanda detector. This is an amazing device. It's 50,000 tons of water in a mine, in a working mine in Japan. And these are physicists in a little boat floating on the water as it's filling up. This is kept in the dark. It's kept with the cleanliness of a laboratory clean room, so there's no radioactivity in it. It's surrounded by 11,000 phototubes, and it's kept in the dark. And what was it designed for? Well, it turns out if the forces of nature unify at this incredibly small scale, then I am sorry to say, and I've noticed a number of people will be depressed about this looking at their hands, that diamonds aren't forever. Okay? Because it turns out if the forces of nature are unified, even protons are unstable. The fundamental particles that make us up. And we calculate the lifetime. If it occurred then, the lifetime of a proton should be about 10 to the 33 years. So you don't have to worry. Now, you might say, well, 10 to the 33 years is a long time, which is true. But it reminds me of a Woody Allen joke, but I'm not going to tell it. And so it's much longer than the current age of the universe, which is 10 to the 10th years. It's 10 billion years. So it's irrelevant to us. But the laws of physics are probabilistic, as Jerry was pointing out in some sense, quantum mechanics anyway. So the average proton lives 10 to the 33 years in this prediction. But if you were somehow to bring 10 to the 33 protons together in a room, then on average one of them would be expected to decay each year. Okay? So where can you get 10 to the 33 protons? 50,000 tons of water. So this experiment was built in the 1970s in the heyday of grand unification, and it was put aside and put in the dark, and it's been operating for 20 years, and we haven't seen a proton decay. Now, the challenge here, this is why I'm a theorist and not an experimentalist, the challenge is great because you might expect one proton decay every 10 years or 5 years or something like that, but if the experiment's offline for the minute when that happens, you've got to wait another 10 years, okay? So it's a really hard experiment to do. The fact that it hasn't seen anything, well, maybe it was offline, or it turns out when you put supersymmetry in the mix, the scale of grand unification goes up a little bit, and you'd expect one decay every 10 to 30 years, and so maybe it's going to happen. So the point is that this is still operating. It might be that we will see a signal. When a proton decays, it will produce a flash of light, and this experiment might be able to actually probe grand unification on another scale. The other place, of course, is the Large Hadron Collider itself, the most complicated machine ever built by humans. One of the greatest. This is the Gothic cathedral of the 21st century. It was created by thousands of, just like the Gothic cathedrals, which were then built for the beauty of God. This is to understand the beauty of nature. But just like they were built over centuries, this was built over decades by thousands of physicists from hundreds of countries, speaking dozens of languages, dozens of religions, but they all work together to build these things to an accuracy, machines that require accuracies of a millionth of an inch. This is something called the compact muon solenoid, which I have a better picture of it because it has me in it, but it doesn't show it as much. It's built in two halves. Each half has more iron than in the Eiffel Tower. And just to give you a sense of this, the magnetic fields that are used here are so great. These two halves are sitting on the ground. Each of them is more than 20,000 tons. And the magnetic field is so great that if it were turned on when they are apart, it would actually drag them together. Okay? And the machine itself is 26 kilometers at a temperature of almost absolute zero with liquid helium, the largest superconducting magnets in the world, with a vacuum that's greater than the vacuum of space. There are fewer particles in that tunnel than there are in empty space outside the Earth. It's amazing. And these detectors, all designed to try and explore the fundamental structure of matter. And it could be, for example, now that the Large Hadron Collider is turned on, many people hope that we'll see these particles due to supersymmetry. A whole slew of new particles. If that's true, in fact, most of us thought we'd see them before the Higgs particle. Most of us would have bet it's a lot easier to see them than the Higgs. The fact that we haven't seen them is worrisome or interesting, depending upon your attitude. Important. I'm still hoping they're not there, even though I hope they're there. Because if they're not there, it means all our ideas are wrong and there's something more interesting to discover. But if it turns on, it'll tell us supersymmetry exists. If it discovers them, that'll tell us, give us more evidence for grand unification, and again support this idea. So it'll tell us if we detect gravitational waves, we'll be able to probe the nature of inflation at a time that we might be able to detect in some sense indirectly with these other detectors. But it'll allow us to probe the physics of the universe when it was a millionth of a billionth of a billionth of a billionth of a second old directly, essentially the beginning of time. But more than that, it will allow us to probe for the existence of other universes. I find that fascinating because I've written about the multiverse. And everyone always says, well, that's just religion. That's scientists having faith in something because they don't like God. And as you probably heard if you heard on the unbelievers, it's true, I don't like God. But we didn't invent the multiverse because we didn't like God. We invented the multiverse because physics suggests that it actually exists. That unfortunately, and I mean unfortunately because I don't like it, the laws of nature in our universe may just be an accident. And there may be many universes with different laws of physics. And why? Well, inflation predicts that. Because remember, I told you what happened is inflation is this phase transition, and in one place suddenly, boom, that phase changes. But just like icicles on that window I was telling you about before, in different regions of the universe, the phase transition might not have even completed. So the space between us and those regions is still expanding ever faster. But in some other place in what we would have called the universe, boom, inflation ends, but it can end in different ways. Just like the icicles can point in different directions, the phase transition that happens in inflation can produce three different forces that are very different in different universes. What we'd call now different universes because they're separated. We'll never be able to detect them because they're farther away and expanding away from us faster than the speed of light. But inflation generically predicts that there will be many, many universes, many regions which leave inflation at different times in different ways, and in each such universe the laws of physics could be different. And in some universes there are a lot of stars, in other universes there aren't any. Another artist image, these are both I think from my Scientific American article, but some of them, some universes have no stars because the laws of nature don't allow stars. We would find ourselves living in one with stars and planets and carbon and nitrogen and oxygen and all the things that are created by stars. And therefore, the fact that our universe appears to be conducive to life is not evidence that their universe is fine-tuned for life, but rather, as Darwin discovered, as far as biology is concerned, life is fine-tuned for the universe in which it lives. Life evolves on Earth to live in the environment in which it finds itself. Otherwise, it doesn't evolve. It doesn't reproduce. Similarly, we find ourselves living in a universe that's acceptable for our existence. It would be fascinating to find ourselves living in another universe. But we haven't. But the interesting thing is, this is just an idea that we have. If inflation happened, grand unification happened, all that stuff. But if we detect gravitational waves from the Big Bang, from inflation, we will be able to test that idea. We'll be able to probe the theory itself, see if it predicts many universes, and even though we'll never be able to detect those otherwise, we'll know they exist in the same sense that in the early 1900s, physicists and chemists eventually realized, in fact, after Einstein, that atoms exist. Einstein was really the first person to show that atoms existed by his thesis on Brownian motion. But no one ever thought you'd ever see an atom. In fact, there were good arguments you'd never be able to see atoms. Now we've been able to get around those arguments. But no one doubted their existence because the same theory that predicted atoms existed could be tested by a whole bunch of different observations. And so if it makes 100 different predictions and they're all right, you're willing to believe the one prediction that you can't test. Similarly, if we can test inflation and we can explain why there are three forces in nature and why grand unification happened, why the proton is 2,000 times heavier than the electron, and all of those things, then the fact that it also predicts other universes that we can't see will be at least highly plausible. Scientifically, it won't be metaphysics. It's not religion. It also, for reasons I won't want to describe, because I want to leave time for, you have some time for questions. It also, as a colleague of mine just showed, actually will allow us to test something that also we thought we'd never be able to test. In fact, my friend and colleague Freeman Dyson, who is this contrarian, has argued that there's no test we could ever do to prove that gravity is a quantum theory. Because if gravity is a quantum theory, then the particles that transmit gravity are called gravitons, just like the particles that transmit electromagnetism are called photons, and we can measure photons. But he pointed out brilliantly, because he's brilliant, that if you wanted to build a detector to detect individual gravitons here on Earth, the detector would collapse to form a black hole before you could do the experiment. So he said, we'll never know. It turns out, as we showed, the universe is a detector. Because it turns out that it's quantum processes that produce the gravitational waves that we would see. And we can prove it for mathematical reasons I won't tell you. So if we detect gravitational waves from the Big Bang, then gravity is a quantum theory. And we know there's a big problem that we need to solve. So I want to conclude by saying, oops, well, that was a picture again. I'll conclude with Virgil. These are the tears of things and the stuff where mortality cuts us to the heart. When you think about the universe, when we look at that Hubble space image, it causes us to think about our own existence. And I find it remarkable that in less than a human lifetime from the time Hubble first, in fact, discovered the universe expanding, and we could see the fact that there were other galaxies, that we have come, using the techniques of science, to this threshold of maybe seeing back to the very beginning of time. And the beauty of it, as I say, points out a number of things. One, the fact that science works. The fact that you can bring people together of very different cultures and make it work. And two, this beauty of the fact that what we really care about is what the right answer is. The fact that we haven't seen gravitational waves yet is intensely disappointing to me as a scientist. And it was incredibly disappointing to the people at BICEP who felt very embarrassed. But what they did was try and find the right answer. And that's what we have to keep doing. Whether we like it or not, we want to learn how the universe works. And whether this beautiful picture I presented for you holds together or not will depend on observations we make. And if it's all wrong, great. Thank you very much.